For multi-class classification, we typically use a loss function known as the cross-entropy loss. I won't get into the exact details of why we use it here because it gets very mathematical, but I'll show you what it looks like and point out some of the important properties that it has. So when we make predictions for multi-class classification problems, we're going to be predicting a probability distribution over all of those classes. We want to push up the probability predicted for the correct class, the label, and by doing that, we're going to push down the probabilities for all the incorrect classes, because together they have to sum up to 1, because they represent the probability distribution over those different classes. And we're going to attempt to achieve that by minimizing a loss function. So here, I've got the probability predicted for the true class. And in a perfect prediction, the probability of the correct class is 1, and all the others are 0. And at that point, I should have 0 loss. So I know that my loss function is going to need to go through this point of the graph. And that's where the probability is equal to 1. And in the worst case, our loss should be as large as possible. And so you can imagine, as the probability predicted for the correct class gets closer to 0, the loss function should get larger and larger and larger. It could look something like that. What I've drawn there is asymptotic to the probability equal to 0. So when the probability of the true class is predicted as 0, the loss would be infinite. And the equation for a curve like this could be the negative log the probability predicted for the true class. And this is the cross-entropy loss function. That is the negative log of the probability predicted by your model for the correct class. So this is what comes out of the model. That's the probability which your model predicts that the example you gave it is a member of the class which its label says it is. So just to make that crystal clear, your model is going to take in some input, features x, and produce a prediction y hat. In a multi-class classification setting, that is going to be a vector. It's going to be a vector of different probabilities which represent the probabilities for the different classes. And if the label is 2, in this case, which would be this index with this probability, then this is the probability which you're going to put into the cross-entropy loss function. So the cross-entropy loss for that particular example will be negative log 0.6, something like this. Now I know what you're thinking, there's probably a number of different functions which could also have this shape, so why is it exactly this negative log probability? Well, it can be derived mathematically as well, but I won't go into it here because it gets a bit over detailed, so I'll show you that later. You should notice a few important things about the cross-entropy loss function. Firstly, it's smooth and differentiable, and that means that you can calculate loss functions and then differentiate through those loss functions all the way through to the model parameters which you want to update using gradient descent. Secondly, the probability which you take from the output distribution and put into this function depends on the label for the specific example. So like I said here, the fact that I take this probability and put it into the negative log function is because that's what the true label is. If the label were different, if it was 0, then I would take this probability and put it into that function. And the third thing, which I think is really important to understand, which relates directly to that, is that you don't need to explicitly push down the other probabilities, as long as you push up this probability by minimizing this loss function. And that's because all the probabilities have to sum up to 1. So if you try to maximize the probability for the correct label, then by default, you're going to be pushing down the probability for all of the incorrect labels. And so all you have to do is minimize the cross-entropy loss for the true example label. And minimizing that loss will push up the probability for the true class being predicted for that example. If I was going to implement the cross-entropy loss function in Python, it might look something like this. So I'm going to use it something like this. This is typically what you have. You have a cross-entropy loss function which takes in a vector of probabilities, the distribution over the predicted classes, and then has an index as the class label. And what we can do is get the probability of the true class by indexing the predictions with that target. and then return the negative log of the probability predicted for that true class. And I'd need to pass in the predictions and the labels here. And then when I print the result, I get this back as the loss. If I change the label to a 0, meaning this is the probability predicted for the correct class, then the loss is going to be much higher. And as that gets smaller, the loss increases. And when I predict the true class with perfect confidence, I get 0 loss. This is a really important loss function to understand if you want to be able to build models from scratch or optimize existing ones, because a huge number of problems can be framed as multicast classification problems, and they're going to be trained by minimizing this loss function.